Welcome to the Explainer. Today, we're popping the hood on your computer. We're going to dive straight into the microscopic traffic mechanics of processors. We're talking about how they handle massive data traffic jams at a microscopic level through some really elegant hardware solutions, things like stalling and forwarding.
Okay, let's ground this with something we all know: doing laundry. The source material uses this brilliant analogy. It says, if the washer takes a longer time than the dryer, well, then the dryer has to wait. It's just a simple, undeniable rule of household chores, right? But honestly, it hits the nail on the head perfectly for the fundamental logic we're exploring today.
So that actually brings up a really intriguing question. How exactly does a microchip handle its own kind of laundry jam? See, inside a processor, the laundry is just this continuous, endless stream of instructions, and we need to figure out how the system manages that flow when one single instruction takes way longer than the next, because if it doesn't handle it right, the entire system backs up.
Section 1. The 5-stage MIPS pipeline. Let's get right into it.
All right, stepping directly into the processor's physical data path, execution is broken down into a strict 5-step pipeline. We've got instruction fetch, decode, execute, memory access, and write back. 1, 2, 3, 4, 5. This rhythm? It's literally the heartbeat of your computer. And if we trace an instructions flow from left to right here, it reveals how discrete actual physical sections of the hardware correspond exactly to those 5 steps we just talked about. It's basically this incredibly precise microscopic assembly line from math.
Now, what's really fascinating is mapping those 5 physical steps into perfectly timed, sequential clock cycles. Just look at this beautifully synchronized flow. As soon as the very first instruction moves to decode, boom, a second one instantly enters fetch. It maximizes efficiency, kind of like cars smoothly merging onto a highway without ever having to hit the brakes.
Moving on to Section 2, identifying pipeline hazards. Of course, the real world is almost never perfectly synchronized, is it? When this beautiful computational flow gets interrupted, we get what engineers call hazards, and these require immediate problem solving. First up, we have structural hazards. The source defines this as existing when a single hardware resource is accessed for 2 different operations in the exact same clock cycle. Imagine 2 cars trying to park in the exact same parking spot at the same time. Total disaster. Luckily, our classic 5-stage MIPS pipeline avoids this specific hazard gracefully by having totally separate register read and write ports, so reading and writing can happen simultaneously, completely crash-free.
But then we run into data hazards, like read after write dependencies. These are actually proactively checked early on during the decode stage. They pop up simply because different mathematical operations have varying latencies. They take different amounts of time. Think about it. If a later instruction absolutely needs the result of a previous one, but that previous one hasn't finished writing its result yet, you've got a conflict. Now, a lot of times the pipeline solves this brilliantly using something called forwarding. This is where the hardware just bypasses the wait entirely and routes the result straight from the execute stage directly back to the next instruction before it's even officially written down to the register. Pretty clever, right?
Section 3. Stalling for dependencies. Let's look at what happens when forwarding isn't quite enough. Yeah, sometimes even forwarding can't save the day. Imagine we've got a floating point division instruction, a DIVD. Division is a beast. It's complex and takes many cycles. If the very next instruction is an addition, an AD.D, that desperately needs the result of that division, the pipeline basically hits a brick wall. The processor fetches the division in cycle 1, fetches the addition in cycle 2, but in cycle 3, it realizes the dependency just cannot be forwarded in time, so the processor is forced to deploy its brute force emergency solution, a stall. It literally freezes the addition instruction in place while it waits.
So, following the processor's decision-making process here for branch checking and fetching operands, you can clearly see that when a hazard forces a stall, the entire pipeline behind it essentially just pauses. The flow is totally interrupted, waiting for that necessary data to resolve. Going back to our analogy from the beginning, the dryer, which is our AD instruction, is simply sitting there waiting for the washer, the div instruction, to finally finish its longer cycle.
Section 4. In-order versus out-of-order execution.
Not stalling works, sure, but it leaves massive parts of the processor sitting completely idle, just wasting precious computing time. So, shifting away from simple in-order execution, where instructions just stubbornly stall in their exact original program sequence, modern architectures evolved to use out-of-order execution. This is where the hardware actually rearranges the execution sequence on the fly just to eliminate those unnecessary waits.
And this magic? It's achieved through what the source material calls dynamic scheduling. Think of the hardware acting as this highly intelligent, super-fast traffic controller. If an instruction is stuck waiting for data, dynamic scheduling literally changes the control logic. It says, okay, you wait here, delaying the stuck instruction, but actively looks ahead, finds later non-dependent instructions, and issues them right away. It is essentially pulling cars out of a traffic jam and routing them forward to keep the overall processor moving at top speed, which mitigates those read and write hazards incredibly efficiently.
So we've gone from a simple washer and dryer rule all the way to an incredibly complex execution engine, dynamically routing and forwarding microscopic traffic to avoid stalling out. Which really leaves us with a fascinating thought to take away. As we stack billions, literally billions, of these instructions together every single second, how do modern multi-core processors scale these exact same microscopic traffic management principles to achieve the insane speeds we rely on today? Thank you so much for exploring this explainer with me. Let that question spark your curiosity. Until next time.